There is a question that never quite leaves you once it finds you. It arrives quietly, usually late at night, when you find yourself staring at a map of the world. You trace the coastlines with your eye, the eastern edge of South America, the western bulge of Africa, and something stirs. A feeling not quite like recognition, but close to it. The shapes almost fit. The curves almost mirror each other. And then the thought forms, slow and enormous. What if these two land masses were once pressed together, side by side, touching? What if the ocean between them is not a permanent feature of the world, but merely the latest chapter in a story that began hundreds of millions of years ago? That question has an answer. And tonight, we are going to follow it all the way back. This is not a story about things that happened long ago and no longer matter. This is the story of the very ground beneath your feet, of the mountains that frame your horizon, the rivers that cross your continent, the creatures whose ancestors learned to breathe and walk and hunt and die across a world that looked nothing like ours. Everything you have ever stood on, every shoreline you have ever seen, every storm that has ever formed above your head, all of it traces back, eventually, to a single extraordinary arrangement of land that existed on this planet for tens of millions of years. A supercontinent. One vast, unbroken mass of rock and soil that held nearly all the land on Earth in one place, encircled by a single immense ocean. It had no borders, no dividing seas, no distant continents rising from the waves in every direction. There was only one world, and we call it Pangea. To understand what Pangea actually was, not just as a diagram in a geology textbook, but as a real, breathing, violent, living world, you have to first let go of the map that lives in your mind. Erase the Atlantic. Close up the gap between Africa and the Americas. Push Antarctica northward and bring India back to rest against the eastern shoulder of that great southern landmass. Let the Mediterranean shrink and the Arabian Peninsula press back into Africa. Watch Europe lock against North America along a seam that runs through Scotland and Newfoundland. Keep going until there is nothing left but one enormous shape stretching from pole to pole, surrounded on all sides by a single global ocean so vast it covered more than 2/3 of the planet's surface. That ocean had a name too. We call it Panthalassa, and together Pangea and Panthalassa were the entire world, the complete inventory of land and sea, laid out in a configuration so different from today's that a satellite photograph of that ancient Earth would look to our eyes like an image of an alien planet. But before we can stand on Pangea and feel its ground beneath us, we have to understand how it came to exist. Because Pangea was not the beginning. It was not even the first supercontinent. The Earth has been assembling and disassembling its continents for billions of years in a slow, grinding cycle that makes even the age of dinosaurs seem like a recent event. Long before Pangea, there was a supercontinent called Rodinia, assembled nearly 1 billion years ago. It broke apart, its fragments scattered across the globe, and for hundreds of millions of years, the planet was a patchwork of separate land masses drifting across the face of a world almost entirely covered in ocean. Then the drift reversed. Slowly, pulled by forces rising from deep within the Earth's mantle, those fragments began to converge again. They were not rushing toward each other. They moved at speeds measured in centimeters per year, rates so slow that no living creature could ever perceive them. Yet over millions of years, they reshaped the entire face of the planet. The mechanism behind this movement is a process we now call plate tectonics. The outer shell of the Earth is not one solid piece. It is broken into enormous slabs, the tectonic plates, that float on the hotter, partially molten rock beneath them. Heat rising from the planet's interior creates convection currents in that deeper layer, and those currents drag the plates along with them. Where two plates collide, the results are dramatic. Mountain ranges buckle upward, volcanoes erupt in chains. The ground shakes with earthquakes that echo for thousands of kilometers in every direction. Where plates pull apart, the crust stretches thin, valleys sink, and eventually the ocean floods in to fill the gap. This is the engine that built Pangea, and it is the same engine that would one day tear it apart. By around 300 million years ago, the process of convergence was nearing its conclusion. The major land masses of the time, Laurussia in the north, which would eventually become North America and Europe, and Gondwana in the south, the immense southern continent that held the future shapes of South America, Africa, Antarctica, Australia, and India, were on a long collision course. Between them lay older oceans that were slowly being crushed out of existence as the plates pressed together. One of these was the Reich Ocean, a body of water that had separated the northern and southern landmasses for hundreds of millions of years. As it narrowed, the seafloor at its edges was dragged downward into the Earth's interior in a process called subduction, and the ocean shrank decade by decade, millennium by millennium, until the moment came when the two great land masses finally met. When they did, the collision was not like two ships bumping gently against a dock. It was like two enormous slabs of rock grinding into each other at a pressure almost unimaginable in human terms, crumpling the crust along their leading edges the way a tablecloth crumples when you push it across a flat surface. The result was mountain ranges that rivaled the Himalayas of today, towering stone walls thrown up along the suture lines where the continents fused. The remnants of those mountains still exist. The Appalachians of eastern North America and the ranges of Scotland and Morocco are all relics of the same ancient collision. They were once the same mountain range, part of a single continuous ridge that ran along the central seam of Pangea when the supercontinent was young and whole. That seam, that ancient scar where Laurussia and Gondwana pressed together, is still legible in the rock record if you know how to read it. By approximately 270 to 250 million years ago, the assembly was complete. Pangea had formed. Nearly all the land on Earth occupied one connected space. If you could have approached this planet from space and looked down at its surface, you would have seen something at once familiar and deeply strange. One enormous landmass sitting mostly in the eastern hemisphere as we define it now, stretching from the frozen south to the frozen north, its spine running roughly along what would one day become the equator, its eastern edge facing the vast Panthalassan Ocean, its western edge partly enclosed by a smaller sea, a remnant of the older Tethys Ocean that had not yet fully closed. That smaller sea, the Paleotethys, represented the last memory of the world that existed before Pangea. Its shallow waters, sheltered from the full force of Panthalassa's currents, would prove to be one of the richest environments for marine life in the entire history of the planet. But we will return to the ocean. First, let us go ashore. To stand on Pangea would have been to stand in a world without comparison in all of human experience. The first thing you would notice, before the strange plants, before the unfamiliar animals, before the different quality of the light, would be the sheer scale of the land around you. On the modern Earth, you are never far from an ocean. Even in the deepest continental interiors, the distances to the sea are measured in the hundreds or perhaps a few thousand kilometers. Moisture from the oceans reaches almost everywhere, softening the climate, feeding the rivers, keeping the air from drying out completely. On Pangea, this was not true. The interior of the supercontinent was so vast, so enormously distant from any coastline, that the ocean's influence simply could not reach it. If you stood in the heart of Pangea, you would have been surrounded by land in every direction for distances that would take months on foot to cross. The air would be dry, the sky would be pale with heat, the ground would radiate warmth long after the sun had set, and the silence, except for wind, would be absolute in a way that has no modern equivalent. This deep interior was dominated by one of the largest desert systems the Earth has ever produced. Modern deserts like the Sahara seem vast, but the arid heart of Pangea made them look modest. Geologists have found the evidence of this ancient dryness preserved in the rock record as red beds, layers of iron-stained sandstone that formed under conditions of intense heat and minimal rainfall. These rocks exist today on continents separated by thousands of kilometers of ocean, and they match each other perfectly in age and composition, a mute testimony to the time when all of them were part of the same enormous dust-red interior. In some regions, these deserts may have stretched for 5,000 kilometers or more in a single direction. The wind that moved through them carried fine dust from one horizon to the other. Sand dunes built and rebuilt themselves over millions of years, leaving behind structures of cross-bedded stone that geologists now find buried beneath modern cities and farmland, ghosts of a world where the wind was the only constant. Life in this interior was not absent, but it was reduced to its essential forms. Plants grew where they could find water, their roots driving deep into the rock in search of moisture trapped far below the surface. Low, spiny, drought-hardened vegetation clung to the margins of temporary riverbeds that flowed only after rare storms. Animals that lived here were built for scarcity, compact bodies that conserved water, behavioral strategies that minimized exposure to the punishing daytime heat, physiologies adapted to extract every last drop of nutrition from food that was always in short supply. To live in the heart of Pangea was to live at the very edge of what life could endure. And yet, life endured. It always does. The contrast between this arid interior and the edges of Pangea was one of the most dramatic environmental gradients in the history of the planet. Move toward the coastlines, and the world transforms. The ocean winds that had been stripped of their moisture long before reaching the interior now arrived at the coasts, carrying everything they had picked up from thousands of kilometers of open sea. Rainfall was heavy and regular. Rivers ran full year-round. The vegetation thickened from sparse and stunted to dense and towering, and the life that filled those coastal forests was extraordinary. The forests of Pangea were unlike any forest that exists today. They were built from species that have long since vanished from the earth, plants that evolved in an age before flowering trees existed, before grasses covered the plains, before the familiar shapes of modern vegetation had yet been invented. Towering above everything else were the seed ferns. Not true ferns, but seed-bearing plants that wore their reproductive structures on enormous spreading fronds. Their canopy could be dense enough to reduce the forest floor to near darkness even in the middle of the day. Among them rose the early conifers, the ancestors of today's pines and spruces and firs. But in the Permian, they were still pioneers. Their needle-like leaves adapted to a wider range of climates than most of their contemporary plants. Closer to the water's edge, in the swampy lowlands where rivers spread out across their floodplains before reaching the sea, forests of ancient horsetails and club mosses grew in dense stands, their hollow jointed stems forming corridors of green above the waterlogged ground. These forests were the lungs of the supercontinent. Their leaves pulled carbon dioxide from the atmosphere and released oxygen in return. During the period just before Pangea reached its final form, the Carboniferous period, the oxygen they produced may have raised atmospheric levels to nearly 30%, compared to 21% today. That extra oxygen had consequences that are almost difficult to believe. Insects breathe not through lungs, but through a system of tiny tubes that carry oxygen directly to their tissues through diffusion. In normal air, this process limits how large an insect can grow. But in air rich with oxygen, that limitation is relaxed. The insects of the Carboniferous and early Permian grew to sizes that seem impossible by modern standards. Dragonflies with wingspans approaching a meter cruised through the humid forests on wings that caught the light like stained glass. Millipede-like arthropods stretched to lengths of 2 meters or more, their many legs rippling in slow waves as they moved through the leaf litter. These were not evolutionary oddities. They were the logical products of an atmosphere that had been changed by the forests themselves, a feedback loop between plant life and air chemistry that produced a world governed by different physical rules than the one we inhabit. The atmosphere of Pangea was always in motion, always changing, always cycling through compositions that shifted with the volcanic activity, the spread of forests, the burial of carbon in the great swampy lowlands that would one day become coal. Those coal seams, mined today across Europe, North America, and Asia, are the compressed remains of the forests that stood on the coasts of Pangea. Every piece of coal that has ever been burned to heat a home or generate electricity is a fragment of those ancient trees, a small portion of the biological material that once made up the living edge of the supercontinent. To burn coal is, in a very literal sense, to release the stored sunlight of a world that existed before the dinosaurs. Volcanic activity was constant across the entire age of Pangea, and its effects reached into every corner of the supercontinent's existence. Along the fault lines where the tectonic plates still shifted beneath the newly assembled landmass, magma pushed upward through the crust, feeding chains of volcanoes that stretched for thousands of kilometers. Some of these eruptions were gentle and slow, releasing lava that spread in thin sheets across the land and built up vast plateaus of dark basalt over millions of years. Others were explosively violent, sending columns of ash and gas into the upper atmosphere where they could circle the planet for years, scattering sunlight and cooling the surface below. Carbon dioxide released by volcanic activity acted as a greenhouse gas, trapping heat and pushing temperatures higher. Sulfur compounds from the same eruptions could produce the opposite effect, blocking solar radiation and triggering brief cold intervals. The climate of Pangea swung between these competing forces in ways that left their marks on the fossil record as clearly as the bones of the animals that lived through them. The mountain ranges of Pangea deserve their own attention because they were not merely scenery. They were active participants in everything that happened on the supercontinent. The Variscan Mountains that ran along the central suture of Pangea, where Laurussia had welded to Gondwana, were at their height comparable to the Himalayas today, their peaks perhaps reaching 5,000 or 6,000 meters, permanently snow-capped, their glaciers feeding rivers that flowed outward in every direction toward the coasts. These were young mountains, their rocks still being pushed upward by the compression that had created them, their slopes steep and unstable, prone to the enormous rock slides and debris flows that characterize high mountain environments where erosion is more rapid than the uplift that created the relief. Over millions of years, they would erode, their peaks worn down, their debris spread across the plains around them in thick sedimentary sequences that preserved in their composition the entire story of what the mountains were made of. But in the early Permian, they were grand, cold, and formidable. The presence of these mountains had effects that extended far beyond their own slopes. They created rain shadows that turned vast regions of Pangea into desert. They acted as barriers to the movement of animals and plants, creating evolutionary divides that separated populations even on the same unbroken supercontinent. They generated their own local climates, cooler, wetter than the surrounding lowlands, supporting forest communities that differed from those on the plains below them. And they were sources of enormous quantities of fresh water, their glaciers and snowfields feeding rivers that constituted the arteries of the supercontinent's ecological system, connecting highland to lowland, interior to coast, in a web of flowing water that no desert or plain could entirely interrupt. The volcanoes that accompanied the mountain building were no less consequential. Each major eruption was a geological event, but it was also a biological event, a sudden introduction of gases and particles into the atmosphere that could alter weather patterns, deposit minerals on distant landscapes, and in extreme cases, produce enough aerosols to cool the planet for years. The fossil record shows the effects of these eruptions in the growth rings of ancient trees, preserved in petrified wood. Years of normal growth interrupted by narrow rings that represent cold summers when volcanic aerosols reduced incoming solar radiation, followed by a return to normal growth when the aerosols settled. These are not inferences, they are measurements. The trees of Pangea recorded the volcanic calendar of their age in the structure of their own wood, and we can read it 250 million years later in the silicified rings of specimens recovered from formations on 4 different continents. The interaction between volcanic activity, mountain building, atmospheric chemistry, and biological life was not a series of separate phenomena. It was a single integrated system with feedback loops running in every direction. Forests drew down carbon dioxide and cooled the climate. A cooler climate reduced chemical weathering of rocks, which reduced the consumption of carbon dioxide by that process, which allowed volcanic emissions to accumulate more rapidly, which warmed the climate again. Mountains eroded, and their minerals fertilized the oceans. A more productive ocean drew more carbon dioxide from the atmosphere. Less carbon dioxide meant a cooler climate and slower weathering. Every component of the Pangean world was connected to every other component through chains of cause and effect that ran through the atmosphere, the ocean, the rock cycle, and the biosphere simultaneously. The Earth was not a collection of separate systems. It was, and is, one system, and Pangea, in its scale and its duration, illustrated that more clearly than any other configuration the planet has ever produced. But it was not only the volcanoes that shaped the atmosphere. The arrangement of Pangea itself, One enormous landmass surrounded by one enormous ocean created atmospheric circulation patterns unlike anything that exists on Earth today. On the modern planet, the continents break up the flow of wind and create complex regional weather systems. Pangea had none of this complexity. The winds that formed over Panthalassa could travel for thousands of kilometers across the supercontinent surface without meeting a significant barrier. Warm air rising above the equatorial belt created powerful monsoons that drenched the coastal regions during the wet season and then retreated, leaving the land dry and baking under an intense sun. The scale of these monsoons was extraordinary. Storms that would dwarf anything in the modern meteorological record, carrying rainfall and flooding across regions the size of modern continents, before dying out somewhere in the dry interior, where the last of their moisture evaporated before it could reach the ground. Into this world, its forests and deserts, its monsoon coasts and dust-red interior, its oxygen-rich air and volcanic skies, life had been developing for hundreds of millions of years. By the time Pangea reached its full extent, the land was populated by an extraordinary diversity of creatures, many of them belonging to groups that no longer exist, and some of them pointing toward the lineages that would eventually dominate the planet long after Pangea had ceased to be. Among the most successful land animals of Pangea's early age were the synapsids, a group sometimes called mammal-like reptiles, though that phrase does not quite capture what they were. Synapsids were neither reptiles nor mammals. They were something in between, or rather, something that existed before the distinction between those two groups had yet been established. They were defined by a single opening in the skull behind each eye socket, a feature that gave their jaw muscles more room to expand, producing stronger bite forces and more efficient chewing than most of their contemporaries could manage. This seemingly small anatomical change gave synapsids a significant advantage in the Pangean world. They could process a wider range of food sources, they could generate more power with their jaws, and over time, their skulls became more sophisticated in other ways too, developing the beginnings of the complex dental apparatus that would eventually allow mammals to specialize into niches from insect eating to grass grazing to ocean hunting. What is most striking about the synapsid story is how long it took and how narrow its path was. The ancestors of every mammal alive today, every whale, every bat, every elephant, every mouse, every human being, were small, warm-blooded, fur-bearing insect eaters that survived the Permian extinction by being too small and too adaptable to be the primary targets of whatever killed the giants. There is a lesson in this that the fossil record teaches with remarkable consistency. It is not always the dominant, the powerful, or the most specialized that survives a catastrophe. Sometimes it is the overlooked. Sometimes it is the creature that lives in the margins, the one that can eat almost anything and survive almost anywhere, the one whose very lack of specialization turns out to be its greatest advantage when the world it evolved for suddenly ceases to exist. The mammals inherited a planet that was built over 135 million years by creatures far more impressive than themselves. And then those creatures were gone, and the mammals were still there, and the world was theirs to fill. The diversity of synapsids that populated Pangea was remarkable. At the largest end of the scale, herbivorous forms like the moschops and the various dicynodonts browse through the coastal forests and open savannas, their barrel-shaped bodies housing powerful digestive systems capable of processing the tough, fibrous vegetation of the Permian. Dicynodonts, characterized by a pair of tusk-like teeth and a beak for clipping vegetation, were among the most widespread animals on the entire supercontinent. Their fossils have been found on every landmass that was once part of Pangea, from Antarctica to Russia to India, a testament to how freely life could move across a world with no oceans in its way. One species, Lystrosaurus, would eventually become one of the most abundant vertebrates on Earth in the aftermath of Pangea's greatest crisis. But we are not yet at that crisis. Among the predators, the synapsids produced some of the most distinctive and memorable animals of the Permian world. The gorgonopsids were sleek, powerful hunters with long, saber-like canine teeth that projected from their upper jaws like curved daggers. They walked with their limbs held more directly beneath their bodies than earlier synapsids had managed, a change in posture that made them faster and more efficient on their feet, capable of running down prey across the open ground of Pangea's interior plains. Their skulls, preserved in remarkable detail in the fossil record, show the beginnings of the larger, more complex brain case that would eventually, hundreds of millions of years later, characterize the mammals their distant descendants would become. Watching a gorgonopsid hunt across the dusty floodplains of the Permian interior would have been to see one of evolution's great experiments in motion, a creature poised between an ancient body plan and a future one, not quite committed to either. The early reptiles shared this world with the synapsids, and while they were not yet dominant, they were quietly developing the traits that would eventually overturn the mammal-like animals and place their own lineage at the center of terrestrial life. Reptiles had solved one of the fundamental challenges of life on land in a way that synapsids had not fully managed. Their eggs were enclosed in waterproof shells and amniotic membranes that protected the developing embryo and allowed reproduction far from standing water. This was not a small advantage on a continent where most of the interior was dry desert, where rivers could dry up for months at a time, where the nearest reliable wetland might be hundreds of kilometers away. Reptiles could go where synapsids could not, or at least could go there more successfully. The early diapsid reptiles, the group that would eventually give rise to dinosaurs, crocodiles, lizards, snakes, and birds, were scattered across Pangea's landscapes in forms still small and mostly unremarkable, but already carrying the blueprint of what they would become. Alongside these larger animals, the insect world continued to fill every available niche with extraordinary variety. The giant forms of the Carboniferous were declining as oxygen levels fell through the Permian, but insects were still the most numerous and diverse animals on land by every measure. Primitive cockroaches, beetles, early relatives of grasshoppers, and numerous groups now entirely extinct populated the leaf litter, the canopy, the soil, and the air of every ecosystem on the supercontinent. They were the foundation of most food chains, the link between plant life and the small predators that would in turn feed the larger ones. Without the insects, nothing else worked. This is a fact that remains as true today as it was in the age of Pangea. The ocean that surrounded Pangea had its own staggering complexity. Panthalassa was not a featureless expanse of water. Its shallow coastal margins, the continental shelves that bordered Pangea's immense coastline, were rich with life. Ancient coral and sponge reefs built structures that rivaled in size and diversity anything on the modern Great Barrier Reef. Trilobites, those iconic armored arthropods that had been crawling across the seafloor for more than 200 million years, were approaching the end of their long dominance, but still clung on in isolated populations in the Paleotethys. Ammonites, the coiled-shelled relatives of today's nautilus, spiraled through the water column in forms of every size and ornamentation, their fossils so abundant in certain rock formations that geologists use them as index markers to date the age of the rock with precision. Early sharks patrolled the open water. Primitive bony fish finned through the coastal shallows. The ocean teemed in ways that the word teeming hardly begins to convey, and all of it was connected by currents, by nutrients carried from the land, by the movement of species around the single continuous shoreline of the one great continent, into a marine ecosystem of global reach and extraordinary resilience. What made the Pangean Ocean particularly interesting was its relationship with the land it bordered. On the modern Earth, each ocean basin has its own character, its own current systems, its own temperature profiles. The Atlantic circulates differently from the Pacific. The Indian Ocean has rhythms shaped by its particular geometry and its proximity to the Asian monsoon. On Pangea, there was essentially one ocean, and it developed circulation patterns of corresponding simplicity and scale. The great gyres, the enormous rotating loops of current driven by the combination of wind, the Coriolis effect, and the configuration of the coastlines, would have been vast beyond modern comparison. Warm water from the tropics moved poleward in huge flows that carried heat to the higher latitudes, moderating what would otherwise have been even more extreme polar conditions. Cold water returned from the poles along the deep ocean floor, upwelling along certain coastlines and bringing nutrients from the depths to the surface, creating zones of biological productivity that would have supported concentrations of sea life visible even from the coast of the supercontinent. The tidal zones along Pangea's coastlines were among the most productive environments on the planet. Where the land met the sea in wide, shallow shelves, tidal flats extended for kilometers, their muddy surfaces covered at high tide and exposed at low tide in a daily rhythm that created conditions of intense biological activity. Early amphibians that had not yet fully committed to life on land spent much of their time in these intertidal zones, hunting the invertebrates that buried themselves in the mud. Lungfish-like creatures used their modified fins to push themselves across exposed flats in search of better pools. The boundary between ocean and continent was not a line, but a zone, kilometers wide in places, shifting with every tide, always productive, always contested, always pushing the evolution of the creatures that lived along it toward new strategies for surviving in two worlds at once. Before we leave the land and look out toward the water, there is a voice in this world that deserves more attention than it usually receives: the sky. On Pangea, the atmosphere was not merely a medium through which birds flew or rain fell, it was an active participant in every process that shaped the supercontinent, a fluid layer of gases and particles in constant motion, connecting the deserts to the coasts, carrying the chemistry of one ecosystem to another, and imposing its rhythms on everything that breathed beneath it. To understand Pangea, you have to understand its weather, not just as climate, not just as the broad strokes of wet and dry, hot and cold, but as the daily and seasonal and millennial reality of what it was like to exist under that ancient sky. The great monsoon systems of Pangea were unlike anything in the modern world in their sheer scale. The physics behind monsoons is straightforward. Large land masses heat up faster than oceans, and the hot air over the land rises, drawing moist oceanic air in from the coasts to replace it. In summer, the interior of Pangea would have heated to temperatures that modern meteorologists would struggle to describe. The air above the dust-red center of the supercontinent rose in a column of blistering heat, and the pressure differential it created pulled moisture-laden winds from Panthalassa inward across thousands of kilometers. Those winds arriving at the coast dumped enormous quantities of rain. Then they moved inland, and as they climbed over the coastal mountain ranges, they dumped more rain on the windward slopes and left the leeward sides in dry rain shadows. Then they crossed into the interior, losing more moisture with every 100 kilometers, until by the time they reached the true center of Pangea, they were dry and hot and carried nothing but dust. In winter, the pattern reversed. The interior cooled faster than the ocean, and the pressure gradients shifted. Dry, cold air poured outward from the continental center, sweeping down across the landscapes toward the coast, bringing dust storms that could darken the sky for days and burying everything in fine particles of ancient rock ground down by millions of years of erosion. These seasonal reversals were so dramatic, so much more extreme than anything produced by the fragmented continents of today, that they effectively divided the year on Pangea into two fundamentally different worlds, a wet world and a dry world, separated not by geography, but by time. The storms that formed along the edges of Pangea's monsoon systems would have been extraordinary phenomena. Supercells developing over the warm coastal seas, drawing energy from the temperature difference between ocean and land, building into systems that dwarfed any tropical cyclone in the modern record. Lightning was constant along these storm fronts, not the occasional flash of a summer thunderstorm, but continuous, branching, world-illuminating discharges that connected the clouds to the ground in sustained electrical conversation. In the forests near the coast, these lightning strikes started fires with a regularity that made fire not an occasional disaster, but a permanent feature of the landscape, a cycling agent that cleared old growth and opened space for new communities. The fossils of Permian and Triassic plants show patterns consistent with a world where fire was as normal a part of the environment as rain, where certain plant species evolved their bark and their seed coats and their growth habits in partial response to the likelihood of periodic burning. Even in the calm periods between monsoon seasons, the sky above Pangea was never entirely still. Dust devils spiraled across the interior plains. Dry lightning flickered over the desert at night, with no rain to follow it. The sun, unfiltered by the oceanic haze that softens the light over modern coasts, beat down with an intensity that bleached the rocks and cracked the clay of dried riverbeds into the patterns that geologists call desiccation polygons, preserved in the ancient rock record as unmistakable evidence of a landscape that regularly baked and dried and baked again. At night, the absence of moisture in the atmosphere meant that heat radiated away from the ground with a speed and completeness that dropped temperatures dramatically, producing frosts in some interior regions, even during what would nominally be summer at those latitudes. The extreme daily temperature swings of the Pangean interior are among its most distinctive climatic signatures, recorded in the differential weathering patterns of rocks that expanded and contracted through wide temperature ranges day after day for millions of years until they cracked along those cycles. The rivers of Pangea were vital threads in this ecological fabric. Rising in the mountain ranges that had been built along the supercontinent's ancient collision zones, they carried water and sediment down through every landscape from highland forest to coastal delta. Some of them were enormous by any modern standard, waterways that crossed distances equivalent to the width of entire modern continents, gathering tributaries as they went, building up the broad floodplains where some of the richest ecosystems of the Permian were centered. Along their banks, the density of life was highest, the vegetation thickest, the prey most abundant, the predators most active. Fossil trackways preserved in the ancient siltstones of these floodplains capture moments of life with an intimacy that no other type of evidence can match. The crossing paths of herbivores and predators, the delicate three-toed prints of small reptiles, the drag marks of tails in soft mud, the evidence of individual animals going about their lives on a morning 260 million years ago, unaware that they were on a continent that would one day break apart and scatter their descendants' fossils across half the world. There was something profoundly different about the way evolution worked on Pangea compared to how it works on today's Earth. On our planet, the oceans between the continents act as barriers. Species that evolve on one landmass stay there, separated from their relatives on other continents by hundreds or thousands of kilometers of open water. Over millions of years, those separated populations diverge, adapting to their own local conditions and eventually becoming distinct species. This is why a kangaroo and a rabbit, which occupy roughly similar ecological niches, look almost nothing alike and are not closely related. They evolved on separated continents and arrived at similar solutions to similar problems independently. On Pangea, this kind of isolation was largely impossible. A species that evolved in one corner of the supercontinent could, given enough time, spread to every other corner without ever crossing water. The same predator that hunted in what is now Brazil could follow its prey into what is now China. The same tree that colonized a floodplain in what is now South Africa could send its seeds drifting on the wind to what is now Greenland. Pangea was a single connected stage, and life played out on it with a freedom of movement that the modern world cannot offer. This connectedness accelerated certain aspects of evolution while slowing others. New traits spread quickly. Successful body plans radiated across the entire supercontinent with relatively little of the local adaptation that isolation normally produces. When a new predator evolved that was faster, smarter, or more physiologically efficient than its predecessors, it could compete across the full range of its prey's distribution almost immediately. The arms races of evolution ran faster because the contestants could meet across a wider front. And when mass death came, as it eventually did, as it always does, the survivors spread just as quickly into the emptied landscapes that the disaster left behind. Because the disaster did come, and when it arrived, it was the most complete, most devastating extinction event in the history of life on this planet. Around 252 million years ago, something broke. The most persuasive evidence points to a cause that began deep in what is now Siberia, where an enormous plume of heat rising from the Earth's mantle reached the base of the crust and began forcing its way through. What followed was not a single volcanic eruption, but a volcanic event that continued for hundreds of thousands of years, a series of eruptions so vast in their combined scale that they eventually covered an area larger than modern Europe in lava. We call these eruptions the Siberian Traps, and their geological legacy is still clearly visible across the Russian landscape today. But their consequences in the late Permian were not geological. They were biological, they were catastrophic, and they nearly ended everything. The gases released by the Siberian Traps poured into the atmosphere in quantities that overwhelmed the planet's capacity to absorb them. Carbon dioxide accumulated, and the greenhouse effect intensified, raising global temperatures by 8 to 10 degrees Celsius over what were, in geological terms, astonishingly short periods of time. The warming triggered the release of methane from seafloor sediments and permafrost, amplifying the effect. Sulfur dioxide from the eruptions acidified rainfall, killing vegetation across vast regions. The oceans, warming faster than life could adapt, lost most of their dissolved oxygen in a process called anoxia. The shallow seas that had teemed with life became dead zones, their waters stripped of the oxygen that marine creatures needed to breathe. On land, the forests retreated and then collapsed entirely across large areas, taking with them the entire food chains they had supported. Animals that depended on those forests had nowhere to go. The numbers are staggering. By the time the Permian-Triassic extinction had run its course, somewhere between 90 and 96% of all marine species had vanished. On land, the losses were nearly as severe. Perhaps 70% of all vertebrate species perished, including the majority of the synapside lineages that had dominated the supercontinent for tens of millions of years. The gorgonopsids disappeared completely. Many of the herbivorous mammal-like animals vanished with them. The rich, complex ecosystems of the coastal forests were reduced to scattered, impoverished remnants. The coal swamps that had covered so much of equatorial Pangea died and did not return. In the aftermath of the extinction, the geological record shows a period that paleontologists sometimes call the coal gap, a layer of rock representing millions of years during which the conditions for coal formation simply no longer existed because the forests that made coal were gone. And yet, life did not end. It bent nearly to breaking, and then it held. In the scattered refugees of the devastated supercontinent, in the river valleys where groundwater still flowed, in the elevated regions where temperatures had risen less severely, along the coasts where the ocean still provided some buffer against the extremes, a remnant population of creatures survived. Among them were the small, unimpressive synapsids that would eventually give rise to the mammal lineage. They were not the dominant animals of their time. They had been outcompeted, outhunted, and nearly outsurvived, but they were still there. Among them, too, were the early archosaurs, the group of reptiles from which the dinosaurs would emerge, still small and mostly unremarkable, but positioned to take advantage of a world that had just been emptied of its rulers. The recovery from the Permian extinction was slow by any measure, and Pangea during the early Triassic was a desolate place compared to what it had been. The landscapes that had once been rich with life were sparse and simple. Biodiversity had plummeted to levels not seen since the early history of complex life on Earth. The animals that survived tended to be generalists, creatures that could eat almost anything, tolerate a wide range of temperatures, and reproduce quickly. One such animal was Lystrosaurus, the dicynodont that had survived the extinction in remarkable numbers. For a period of several million years after the catastrophe, Lystrosaurus was the most common large vertebrate on land across most of Pangea, its fossils found in formations from South Africa to China to Antarctica, with a consistency that speaks to a world where diversity had been replaced by abundance of the few. In a landscape emptied of competition, the survivors could spread everywhere, and they did. The early Triassic was in some ways an eerie world. The forests were gone, replaced by sparse assemblages of pioneering plants that colonized the devastated landscapes, much as mosses and hardy grasses colonized the slopes of a recently erupted volcano today. The rivers, their banks no longer anchored by dense root systems, became unstable and braided, shallow sheets of water spreading across wide channels, carrying more sediment than water and depositing it in thick layers that geologists can now identify as the distinctive fluvial signature of a post-extinction landscape. The soils that had taken millions of years to build up under the Permian forests were eroding rapidly with no vegetation to protect them. The landscape had a raw, unfinished quality, not barren, but wounded in the long process of healing from an injury that had nearly been fatal. And yet, within a few million years, the outlines of a new world were beginning to emerge. The archosaurs diversified rapidly into the available ecological space. Some became semi-aquatic hunters, evolving body plans that would eventually lead to the modern crocodilians. Others took to the land as increasingly capable runners, and the lineage that would become the dinosaurs was beginning to produce forms of increasing sophistication and size. By the Middle Triassic, the dinosaurs were already recognizable as a distinct and dynamic group, their fully upright posture and efficient lung systems giving them capabilities that their competitors could not match. By the late Triassic, they had spread across the full extent of Pangea and were already beginning to show the diversity of form and function that would define their 135 million year reign. But the world was not finished with Pangea. Slowly, over the Triassic period that followed the extinction, life rebuilt itself. The archosaurs, free now from the competition of the dominant synapsids that had been so heavily pruned by the extinction, diversified rapidly. One lineage of archosaurs would eventually give rise to the crocodilians. Another would become the pterosaurs, the first vertebrates to achieve powered flight. And a third, the most consequential of all for the subsequent history of the planet, would become the dinosaurs. The first true dinosaurs appear in the fossil record about 230 to 240 million years ago. Small, bipedal animals no larger than a chicken or a medium-sized dog, running on their hind legs with their forelimbs free, their posture fully upright in a way that none of their predecessors had quite managed. They were not impressive by the standards of what they would become, but they were efficient, they were fast, and the world was wide open. Pangea during the later Triassic was a different world from the one that existed before the extinction. The forests had not recovered to their former density, but new plant communities had established themselves, different in composition from those of the Permian, beginning the slow transition toward the gymnosperm-dominated landscapes of the Jurassic and Cretaceous that would follow. The climate remained largely hot and dry across the interior, but the monsoon systems had re-established themselves along the coasts, and wherever rainfall was reliable, life gathered in abundance. The great rivers still ran, still built their floodplains, still served as the highways along which life moved from one part of the supercontinent to another. Dinosaur footprints appear in these ancient river sediments across the world, evidence that within a few tens of millions of years of their first appearance, these animals had already spread across the full extent of Pangea. The oceans, too, were recovering. The marine extinction had been, if anything, more complete than the terrestrial one, but the seas are ultimately more stable environments than the land, less exposed to the extremes of temperature and aridity that make continental life so vulnerable. New reef communities were establishing themselves, built by different organisms than those that had dominated before the extinction. The ammonites, which had been almost entirely wiped out at the end of the Permian, had recovered into a spectacular diversity of new forms, their coiled shells ranging from the size of a coin to the size of a bicycle wheel, their species so numerous in the Triassic and Jurassic that they would become the most precise chronological tools available to geologists dating the rocks of that era. Marine reptiles were entering the ocean, their limbs slowly flattening into flippers, their bodies streamlining, their lungs powerful enough to allow long dives into the productive waters of the recovering sea. The ichthyosaurs, dolphin-shaped reptiles that had returned to the ocean so completely they could no longer survive on land, were already present in the early Triassic, suggesting that the transition to fully marine life had occurred with extraordinary speed in evolutionary terms, a rush to fill the ecological vacuum left by the extinction. And beneath all of this, beneath the recovering forests and the spreading dinosaurs and the rebuilding reefs, the ground itself was preparing to move. The forces that had assembled Pangea had never stopped. Even as the supercontinent stood whole, the heat building beneath it was finding weak points, testing the seams where different continental fragments had been welded together, slowly stretching the crust in certain places where the mantle's convection currents were beginning to pull in new directions. The first signs were subtle, long, narrow rift valleys that appeared in what is now the eastern seaboard of North America and the northwestern coast of Africa. These valleys were no different in their immediate appearance from other tectonic features, and the creatures that lived in them, early dinosaurs, early mammals, crocodile relatives, primitive turtles, had no way of knowing that they were living on the first scratches of what would eventually become the Atlantic Ocean. But the scratches deepened. Lava welled up from below, adding new rock to the valley floors. The valleys widened, and then, with the geological slowness that makes even mountains seem impermanent, water began to seep in from Panthalassa, filling the lowest points of the rift. At first it was shallow, warm, and cut off from the open ocean, a landlocked sea not much larger than the modern Red Sea, which is itself a modern example of the same process at an earlier stage. But it was a beginning. The Atlantic had begun to be born. Pangea was no longer whole. The breakup of Pangea did not happen at once, and did not happen quickly. It was a process that unfolded across tens of millions of years, in stages, with different sections of the supercontinent separating at different times and moving in different directions. The first major split was roughly north-south, dividing the old Laurentian north from the Gondwanan south. Then Gondwana itself began to fragment. South America and Africa started to pull apart. India broke free and began the long northward journey that would eventually carry it into Asia and raise the Himalayas. Australia and Antarctica stayed joined longer, drifting southward together before eventually separating. North America and Europe remained connected for a surprisingly long time, still linked across what is now the North Atlantic, even as the Central and Southern Atlantic was already widening to oceanic dimensions. Each separation had consequences. Where new coastlines formed, new climates developed. Regions that had been deep in the interior of Pangea and starved of moisture now found themselves bordered by young, shallow seas that brought rain where there had been desert. Conversely, areas that had been coastal sometimes found themselves cut off from their oceanic moisture sources as new mountain ranges rose along the lines of separation. The great monsoon system that had dominated Pangea's weather began to break up into the regional weather patterns that govern the modern world. Ocean currents that had circled the entire planet in one vast gyre began to be deflected and divided by the separating land masses. The global climate was being reconfigured from the ground up. The young Atlantic, narrow and warm in its early stages, had a character quite different from the ocean it would eventually become. In the Jurassic, it was essentially a long enclosed sea, shallow, warm, hypersaline, in places where evaporation exceeded rainfall, teeming with marine life that evolved in near isolation from Panthalassa. Along its shores, dinosaurs hunted and fed and left their footprints in the muds that would one day harden into the rocks of the Connecticut Valley and the Atlas Mountains of Morocco. The same species tracks appear on both sides of that early ocean in formations that tell the story of a sea that was still narrow enough for creatures to walk around its northern and southern ends. As the Atlantic widened, those connections were severed. The tracks on the African shore and the tracks on the American shore slowly diverged, belonging to increasingly different animals living in increasingly different worlds, until the separation was complete and the two sides had become separate evolutionary theaters. The mountain ranges that formed along the rifting edges of Pangea were dramatic geological features in their own right. Where the crust stretched and thinned before finally parting, the margins often buckled upward, creating rift shoulder mountains that could reach considerable heights before erosion wore them down. These ranges intercepted rainfall, creating steep gradients from wet windward slopes to dry leeward ones. They channeled rivers into new courses. They created habitats, the cooler, moister environments of the highlands, that differed dramatically from the lowlands around them, and over time accumulated their own distinct assemblages of plants and animals. The rifting of Pangea was not simply a geological event, it was an ecological event of the first order, carving new habitats out of what had previously been continuous landscape, and setting in motion the process of speciation that would produce, over the following hundreds of millions of years, the biological diversity of the modern world. The sediments shed from these rift shoulder mountains recorded the entire history of the breakup in extraordinary detail. Rivers carrying material from the eroding highlands deposited it in the rift valleys and eventually on the floors of the nascent ocean basins. These sediments, red beds and sandstones and shales laid down in ancient river systems, lake beds, and eventually shallow marine environments, form the geological backbone of the Atlantic margins today. When oil companies drill through them in search of hydrocarbons, they are drilling through the autobiography of a continent in the process of division, reading in the composition of each layer the conditions that prevailed when that particular sand or mud was deposited. A red, iron-rich layer means a warm, oxidizing floodplain. A dark, organic-rich layer means a lake where organic matter accumulated faster than it decomposed. A layer of salt means an enclosed basin where evaporation concentrated the seawater beyond the point of crystallization. Each layer is a sentence. The whole sequence is a story. Life responded to these changes in the way it always responds, by adapting, by specializing, and by diversifying into every new opportunity the changing world created. The dinosaurs, which had spread across the whole of Pangea before the breakup began, found themselves increasingly isolated on the separating continents. Populations that had once been connected began to diverge. The same lineage might produce a sauropod giant on one piece of land and a smaller, more specialized form on another, each adapting to its own new conditions without the mixing of genes that had previously kept their populations similar. The biodiversity of the Jurassic and Cretaceous, that astonishing proliferation of dinosaur forms, from the enormous long-necked sauropods to the feathered theropods that would eventually take to the air as birds, was in large part a product of the increasing isolation that the breakup of Pangea was creating. Separation in evolution is one of the greatest engines of diversity, and in the shadow of the dinosaurs, in the ecological margins they left available, the mammals were doing the same thing. The small, mostly nocturnal insect eaters that had descended from the surviving Permian synapsids were quietly accumulating the traits that would make their descendants, eventually, the dominant land animals of the modern world. Warm blood, which allowed them to remain active through cold nights while the ectothermic dinosaurs slept. A larger brain relative to body size, giving them more sophisticated processing of sensory information. Specialized teeth that could handle a wider variety of food sources, and a fundamentally different reproductive strategy, the beginnings of the live birth and extended parental care that would eventually give the mammalian lineage such flexibility in how it raised its young. None of these traits made the early mammals competitive with dinosaurs in the Jurassic or Cretaceous, but they were investments in a future that would eventually, 66 million years ago, suddenly and violently open up. But that is a different story, for a different night. What we are left with tonight is Pangea itself, its memory, its legacy, the ways in which a continent that ceased to exist 200 million years ago still shapes the world you live in with as much force as anything that happened last century. Because Pangea did not simply end, it transformed. Its mountains became the foundations of today's ranges. Its rivers carved the valleys that modern rivers still follow. Its forests, compressed and buried, became the coal and oil that powered the industrial world. Its creatures evolved into every animal alive today, following lines of descent that can be traced back step by step to the creatures that walked its surface. You carry Pangea in your body more directly than you might think. The bones in your hand, the same five-fingered arrangement that appears in every land vertebrate, from lizards to horses to whales, first took that shape in the forelimbs of tetrapods that crawled out of Pangea's coastal waters and onto its shores. The way your diaphragm pulls air into your lungs is a breathing mechanism that traces back to the respiratory experiments of early synapsids in the Permian. Even the way your jaw muscles attach to your skull, that single opening behind the eye socket that defined the synapsid lineage, is a feature you inherited from those Pangean animals that hunted across its dust-red interior and sheltered in its coastal forests. Look at a map of the world today, and you see the pieces of the puzzle scattered across the globe. South America and Africa, their coastlines still unmistakably shaped by the separation that divided them. India, tucked against the underside of Asia in a collision that is still ongoing, the Himalayas still rising by a few millimeters each year as the subcontinent continues pressing northward. Antarctica, sitting alone at the bottom of the world, the last major fragment of Gondwana to find its final resting place. All of them were once one thing. All of them remember, in their rocks, in their fossils, in the ancient magnetic signatures locked into their basalt, the world they were once part of. The plate tectonic cycle that built Pangea and broke it apart has not stopped. It will never stop, not as long as the Earth retains the internal heat that drives it. The continents are still moving. The Atlantic is still widening, the Pacific still shrinking, Africa still splitting slowly apart along the East African Rift. In perhaps 250 million years, a span of time almost incomprehensible from any human perspective, the current continents may have assembled into a new supercontinent. Some scientists call this hypothetical future landmass Pangea Ultima, or Novo Pangea, or Amasia, depending on which model of future drift they favor. They disagree on the details. They do not disagree on the principle. The cycle continues. It has always continued. Pangea was one moment in it, a long moment, extraordinary in its consequences, but a moment nonetheless. This is the most humbling thing that the study of deep time teaches, not just that the world is old, though it is almost unimaginably old, but that it has been old many times before, in configurations so different from our own that they might as well have been different planets. The mountain you can see from your window was once part of a different range on a different continent, raised by a different collision. The coal in a power station was once a living forest in a swamp along the coast of a supercontinent. The oxygen in your lungs was produced in part by those same Permian forests, processed through hundreds of millions of years of atmospheric chemistry to arrive at exactly the proportion that your cells require. The ground beneath your feet is not stable. It is not permanent. It is moving right now slowly enough that you cannot feel it, but moving nonetheless, carrying you along with it through a cycle that has been running since before the first animal left the water and has no intention of stopping. Pangea tells us more clearly than almost any other story in the history of the Earth that impermanence is not a failure. The supercontinent assembled, dominated, shaped everything that lived upon it for tens of millions of years, endured one of the worst catastrophes the planet has ever experienced, and then, slowly, inevitably, completely, it broke apart. And in breaking apart, it did not end. It became something else. It became everything else. It became the world you live in today, still carrying, in its rocks and its rivers and its living things, the memory of the time when all of this was one. We stand on a planet that has forgotten more about itself than we have yet learned. Beneath the cities and the farmland and the ocean floor, the stones remember. They hold in their mineral grains the directions of ancient magnetic poles, the chemistry of vanished atmospheres, the bones of creatures for which we have no living descendants and no adequate modern comparison. Every drilling project that pulls up a core of rock from the deep earth, every outcrop that a geologist chips away at on a mountainside, every fossil that erodes out of a cliff face after a winter storm, all of it is another sentence from a story that has been writing itself for 4.5 billion years and shows no sign of stopping. We are not the end of that story. We are not even close to the end. We are a brief, extraordinary, improbable moment in the middle of it, living on a planet that has been building and breaking worlds long before we arrived, and will continue building and breaking them long after we are gone. But for now, in this particular chapter of that story, we can do something that no other creature in the planet's history has ever managed. We can look back. We can read the rocks and the fossils and the magnetic signatures in the ancient basalt and reconstruct, imperfectly but genuinely, what the world looked like before us. We can stand in our minds on the shore of a Permian sea and watch the gorgonopsids hunt along the riverbank. We can feel the heat of the continental interior, smell the resin-heavy air of the early conifer forests, hear the wind moving through the hollow stems of the giant horsetails in the swamp. We can witness the fire and the darkness of the great extinction and understand, at the remove of 250 million years, just how close life came to ending on this planet. And we can trace the survivors forward through the Triassic, watch the dinosaurs take their first steps across the recovering landscapes, see the first mammals scurrying through the shadows, and know, because we are the evidence, how that story eventually turned out. Pangea is gone, but its echo is everywhere. It is in the mountains. It is in the coal. It is in the matching curves of continents that drifted apart before our species existed. It is in the 5 bones of your hand, and the way your jaw muscles attach to your skull, and the oxygen moving through your blood right now. The world before the world is not somewhere else. It is here, beneath everything, older than the oldest story we have ever told, and still, quietly, steadily, imperceptibly, in motion.